We're going to fix it. Now, we started to look at a few, or we haven't really, we were about to begin at reactions. And again, more on a conceptual way, we started to discuss the importance of bond energies to have an estimate if a reaction should go or not. And now let's just become clear what is the type of argument we are trying to do if we argue and say a reaction should go because the bonds which are forming are stronger than the bonds which we have to dissolve. That's the idea. So typically, if you have a reaction profile, you have starting material and you have products. And if we argue on stability of, or if we argue on if a reaction should work because the products are more stable than the starting materials, the argument which we really look here into is a thermodynamic argument again. Let me see if I find some color. So we have two things to look at. We have to look at the thermodynamic dynamic control. And this is simply the question, is the starting material, or is the energy of the starting materials higher than that of the products? Then if we can overcome an activation barrier, if we put enough energy into this, in an equilibrium, the product should be more stable, so the reaction should be thermodynamically favored. So what we are looking here is the question of delta G, which is the reaction heat of formation. So it's the free energy and the delta G term is composed of two terms, and this has an enthalpy term and an entropy term. And if we look at bond stabilities, is this just the seventh inning stretch, or was this a question? No, only the seventh inning stretch, okay. So, and if we look at bond strengths, forming bonds, dissolving bonds, out of these three, what are we really looking at? Which term are we addressing here? The delta G, the delta H, or the delta S? Who wants to raise his hand for delta G? Delta H? 1. Delta S? Nobody. 98.5% undecided. This has to change, right? You have to make a decision, even if it's the wrong one. So shall we try this again? Delta G? Delta H? Delta S? 75% undecided. That's unbelievable. Guys, you have to, the lecture will go much faster for you if you engage into this. And even if it is wrong, you need to form an opinion. Interestingly enough, we had answers for all three. What we're really looking here, if we argue on bond strengths, is really only the delta H term. The entropy is a measurement for disorder. This is also very often can be estimated. Again, organic chemists are simple people. The way you estimate the disorder is simply you see I'm starting on the, let's say I have a reaction where I react A plus B, and this makes C plus D plus E. So typically you only count the moles and say, okay, I start from two molecules here, I'm forming 3 molecules, entropy is getting bigger, so it should be favorable. If I have the situation A plus B, very often we see this, just makes an addition reaction, makes the molecule C, should be disfavored from the entropy point of view. However, very often we are even in situations where we go A plus B goes to C plus D, when there is on physical, my physical chemistry colleagues would kill me if I say this, but on a first estimation, there's very little entropy change. And so organic chemists, or in organic reactions, very often the T delta S term in the first approximation can be neglected. And so what you're really looking at is simply the change in bond strengths. How much energy do I need to dissolve the bonds on my starting material sides, and how much energy do I gain when I form the new bonds? And in the first estimate, you're doing quite well with this. So you can do this estimation and so again, of the thermodynamic outcome of a reaction, based on delta H, and this is in a good approximation bond strengths changes. But again, it's an estimation. That's the first thing. It neglects entropy. And it does something else. It neglects something else, which is not always too realistic, but still, it's nevertheless a good estimation. What else? Does anyone have an idea what else it neglects? Or it makes another assumption in this very simple analysis. It makes the assumption that the reaction is run in what kind of environment? What kind of environment is this really only true? It makes the assumption that it's a gas phase reaction. So no solvent involved. And we know that in organic chemistry, solvent is extremely important, and it can make a big difference by the way the solvent is able to solvate your product molecules if a reaction goes or not. This is, in this simple analysis, this is neglected. Nevertheless, again, it gives you a pretty good idea if you're on a good way to perform successfully a reaction or not. Okay. And then we have the kinetics. And here we are looking at the activation free energy. So this is the delta G deca here. And this is the same idea just now based on the transition state from the starting materials to the products. You have overcome an energy barrier. Again, this energy barrier is composed from the same terms here, just based on the transition state. And this will tell you if a reaction is kinetically possible and what kind of activation barrier you have to overcome. So this here is the kinetic control. So the kinetic analysis will tell you how fast a reaction is, or if it is even possible, and the thermodynamic analysis will tell you basically how many product molecules with respect to starting materials you will get. And the assumption is here that then we are in a chemical equilibrium. Meaning that basically a thermodynamic control between starting materials, or an equilibrium between starting materials and products, can be established, and then it is only a question of relative stabilities where this equilibrium will be. Okay, so now finally, hopefully, we are looking at a reaction, and a reaction you also, of course, know very well. We wanted to look at the halogenation of alkanes, and let's just start with the let's just in principle start with a reaction here. Let's look at the reaction of an alkane, butane here, and bromine. Something which can be established under photochemical reactions or in the presence of a radical starter, AIBN. You might have heard this. Don't worry, I will write this. I will show this in a moment again. And so the overall outcome here is that you have the bromination, and in this case, there are two possible monobromination substitution products. And HBr is forming. And we are going to analyze this again step by step. You know all this reaction, but what I would like to go is again go through this in terms of these concepts we are discussing. And we are doing this step by step because you will see that this type of analysis is useful for just about any type of reaction. So, if you look at the mechanism, such reactions, we already talked about this last time. In general, radicals undergo a radical chain mechanism. So what you need somehow a start, an initiation, where you form a radical, and in this case, the initiation reaction is the bond scission of bromine, and this can be achieved photochemically into two bromine radicals. And if you look at the bond strengths here, the bromine-bromine bond has 46 kcal per mole. We are using light here. You should be able, and please do this for yourself at home as a small test. You should be able to estimate what kind of light do I need. Do I need UV light, or is visible light still okay in order to cleave such a bromine-bromine bond? And you should come to the conclusion, as you know, that this reaction is being able, you can carry that out by visible light like in the lab, you would use strong normal daylight lamps. In principle, you could do this type of reaction out in the sunlight. And then the important two steps are it's the chain propagation. Let me just do this by showing how the primary bromine product is forming, and analogously the same is true for the secondary one. So you have a radical abstraction of a hydrogen atom forming HBr and a alkane radical. If I want to show this in with reaction arrows, what you should do is, since you are involving bromine, or since you're involving radicals, you use these type of half arrows. And again, keep in mind with reaction mechanisms, these arrows always depict electron movement, never the movement of atoms. So here with the half arrow, you indicate that only one electron is being involved here. And so likewise, you need to use a half arrow here in the direction of the bromine to form the new, or to form the HBr bond. And then another half arrow goes cleaving the hydrogen atom here. And then the second step, completing the chain, would be that this alkane radical is reacting with another molecule of bromine, forming the bromoalkane, and again a bromine radical here. And so this is the typical scenario in the chain propagation. It's always a radical which is present in low concentration reacting with the neutral molecule which is present in high concentration, and only termination reactions which are highly favored from a kinetic and thermodynamic point of view, but which are simply very unlikely. For example, the recombination of two of the bromine radicals, or the recombination of two of the alkane radicals, or the mixed recombination. These would be very fast reactions if the compounds could find each other. However, simply based on concentration arguments, it's much more likely that the radical will react with the neutral compound. So nevertheless, let me write the three possible termination reactions or partners which would be these, simply the radical recombinations. Now, before we analyze this in a little bit more detail now based on the bond strengths, I would just like to show you, and maybe I can draw this next to this one and erase this here. That there is another way to depict such kind of chain reactions. Rather than having like two different equations here, you can really bring this into a type of a cycle. And the way you do this is that you write the two reactive intermediates below each other. And so in principle, what is always happening here is in the first equation, this is your low concentration intermediate, a bromine radical, which is then basically being transformed to HBr on the expense that a new highly reactive intermediate is forming. And these are the two things I have written here. And so this is the chain cycle between the two intermediates, which is really going on. And now, if you look what we need here, we need the alkane, hydrocarbon, which is forming HBr with the radical, with the bromine radical, forming this. And here on the other side, the hydrocarbon radical is reacting with bromine to form the product and is regenerating a bromine radical here. And I kind of like this. I don't know how about you. I don't care how you do it, but so this is of course fine. But I think this depicts very nicely that you alternate between the two reactive intermediates and you funnel in here on the left side starting materials, here on the left side, here on the right side, and you're getting out the respective products. Okay, so let's look a little bit where we are. And for this, let me bring back in your mind some of the, and again, organic people, simple people, relative bond strengths, I think, which you should kind of remember. So CH bond, OH bond, more or less roughly 100 kcal per mole. For the young generation here, you know everything times 4. Nevertheless, I will do kcal all through this class. And so please forgive me. And if you want to write down kcal, multiply by kilojoule multiplied by 4. So that's a CO bond. A CC bond has a little bit less, 90 kcal. It's a little bit weaker than a CH bond. So already just looking at these two bond strengths, that's interesting. Because it will tell you that at least you could wonder immediately why should there be the hydrogen bond abstraction. The CC bond breakage might be even easier. However, of course, we have to take into account also the new bonds which are forming here. So hydrogen bromide, roughly 87. And carbon bromine bond, again, quite a bit lower in this case. So let's just look at these 4. So what is happening here in the first step? So in the first step, we have to break a carbon-hydrogen bond, which will cost us roughly 100 kcal per mole. And we are forming as the new bond here, which brings us 87. If we would have done instead of breaking the CH bond, if we would have broken the CC bond, this would have been 90 here, and then the carbon-bromine bond, which would have been formed, would be 72. Let me see if I can, just as a hypothetical reaction. Put this up there. So basically the alternative here could have been something like this, where you would have formed a carbon-carbon-bromine bond under breakage of the carbon-carbon bond. This would have cost you 90 kcal, and you would have gained roughly 72. So as you can see here, based on this very simple analysis, breaking the CH bond is better simply because you have to bring in more energy, but you also gain more. On the other hand, this is still pretty relatively similar. And of course, a second factor comes in here, and this is the kinetic factor, which will simply tell you that besides of the bond strengths, simply the hydrogens being on the surface of the molecule are much better accessible. So we have the kinetic argument of better access. But again, keep in mind, this is a kinetic argument. This is not a thermodynamic argument. And the very rough analysis I did based on bond strength, again, is the thermodynamic argument. And both of these arguments point you in the same direction, that overall the abstraction of a hydrogen atom should be much better than the abstraction or than the breakage of the carbon-carbon bond here. That there are cases where carbon-carbon bonds are broken, that's a reaction you should also know. That is happening. Does anyone know where this is happening? Typical reaction when you're cracking oil, when you're cracking hydrocarbons, right? And making from longer hydrocarbon molecules oil cracking when you make shorter ones. So usually when you have long hydrocarbon chains as they are present in oil, usually what is being done is it gets heated up, and then indeed the normal reactions you will observe is that you will observe C-C bond fissions. So let me see that I do this right here. And getting radicals, which then can be stabilized by disproportion reactions transferring a hydrogen over here. So this would be a typical cracking reaction of oil, right? And simply what it shows you is that here we are just putting in heat. And the reason indeed that the carbon-carbon bond is now cracking, is undergoing the fission, is simply indeed probably an outcome of the fact that a carbon-carbon bond is indeed a little bit weaker than a carbon-hydrogen bond. But nevertheless, in reactions like this here, involving two reaction partners, the kinetic argument that this one reaction partner is basically can only access the surface of the molecule where the hydrogens are, is basically preventing this or protecting, kinetically protecting the carbon-carbon bond from reacting. Okay, so let's look at here. So we had the situation that we are cracking one bond here, we are forming another one. And so basically, as you can see here, this should be endothermic. You need more energy to break this than you're gaining by forming the bonds. And then here, you already had this number. It's a very low number, 46 kcal, to break the bromine-bromine bond and to form the new carbon-bromine bond is you gain 72 kcals, and so you can clearly see that this is exothermic here. And so basically here, in terms of energy, you have to put in 13 kcal to go from here to here, but here you're gaining roughly, what is it? 26, thank you. You're gaining 26 kcal here in the second step by forming the more stronger bonds. And so you can see that overall, this should be on an exothermic reaction on the thermodynamic argument, and that should therefore work. So let me just bring back in your memory the way to initiate the reaction, radical initiators. So doing this by light is one possibility, but there are also thermal ways, and the two important initiators you should know is AIBN, iso-butyronitrile, And the idea here is that you have this molecule, and you can see that this has built in an extremely good leaving group. Nitrogen, molecular nitrogen, one of the most stable molecules that we know. And so thermally, this is able to form nitrogen, and two of these radicals. And these radicals then can serve as a starting point, for example, to react with bromine to start on, to start like the chain reaction. And the other type of initiators which are also very often used are peroxides. Again, here you're making use out of the very labile oxygen-oxygen bond. And one of the very typical initiators is this dibenzoyl peroxide. It's also abbreviated DPO. This is under thermal condition. It's already enough when the temperature is like 40, also to 40 degrees, so in warm sunlight or so, or 30 degrees even, it starts doing the fission of the peroxo bond. To form this radical here. And this radical, and that's something in general to keep in mind, we will see this a little bit more often. This is basically a radical derived from a carboxylic acid. You know that the carboxylic acids, also aromatic carboxylic acids, are extremely stable. When you go to the Mensa, usually you see, if you read, do they still have the screens where they tell you what's in your food? Very often there is written additive benzoic acid. Right? Why is this in there? Does anyone know? You just go to the Mensa and say, hey, it's fine, benzoic acid. Let's have some benzoic acid. Why do we find so much benzoic acid in our foods? Small quantities? Why? Nobody knows? It's simply to converse your food, right? It has an acidic pH. It kills bacteria, right? So that's also so it's a food preservant. However, the radicals, in difference to the carboxylates, very, very easily eliminate carbon dioxide to form these highly reactive phenyl radicals, and then these start the chain reaction, for example, a bromination reaction. So there are many more, but I think these are the two most important ones. And again, for the halogenation, it is possible to simply use sunlight. Okay, let's look at something. Let's look at something else where we will be able to use the concept of bond strength. Now let's look at, again, the halogenation, bromination, or chlorination of butane. say under visible light conditions. So what I would like to talk here now is I would like to talk a little bit on selectivity. And so the principal two products you should get out here are these two products under elimination of HX. Now, if all the CH bonds would be equal, what kind of ratio would you expect between these two products? If they're equal, there's 50-50 is one answer here.
It's 2 to 3 because I have 6 H bonds in the end and 2 in the middle.
Good point. Another good point. So that's the one thing which is important here. You meant the right thing, it's no question. But you have to take into simply the statistics. How many reaction centers do I have? And indeed, your colleague just said we are having 6 primary. So we're having 6 CHs on the primary. And we are having 4 secondary CHs. So on a purely statistical argument, not knowing anything about stabilities or so the purely statistical prediction would simply argue how likely is it that my X radical is hitting one of the reaction partners, and so therefore we would predict 60-40 here. Chemists like to nominate everything on 100. So 3 to 2 is exactly what you said, but 60-40 is the one thing you would see. So that would be typical. Like you start a research project, right? And you know nothing on anything. This is what you would predict, 60-40. Now you do the experiment. And the first experiment you do is you do the chlorination. And you find that in the chlorination, this reaction is actually not 60-40. It's 29-71. So significantly different from your statistical expectation, in favor even of the one which, based on statistic arguments, you would have predicted to be, which should be forming less. And of course, you immediately know that by the 2 radicals you are forming, you already know the answer because we talked already on radical stabilities. But you know that the 2 possible radicals that are formed here is that the secondary is more stable and that is also reflected in the bond strengths, because we said roughly, I have wiped it out already, but we said roughly CH bonds are 100, but then if you would do the actual measurement, you would find, and you see I have to look this up also, there's no reason to memorize such numbers in detail, right? And also like let's say we do this in a test or so, I think I would give you, maybe if I wanted to see if you're still in the right range, I would say this is 4 kcal more stable than the other one. Give me the range where it is in, right? But there's no reason to memorize this in detail. But so let's say the primary here should be I think it's about 105. And this one should be 101. So and indeed, you will say immediately, less stable, more stable. Therefore, it is easier to break the secondary CH bond. It's more difficult to break the other one. And this is reflected in the product distribution here. And now if we look at this more in detail, so what we are looking here in the moment is the reaction that the X dot is reacting with a primary CH bond and the delta H you would determine for this process is minus 2 kcal per mole. I think this is actually 103. Because I just see now my example here. And so you have the X dot and the C secondary one in the H. And this is delta H should be minus 4. And the analysis we did here is actually, we were looking at, these are the numbers you have for the chlorination. Okay, so we can understand this. There should be an energy difference, and you also know there's this equation. Delta G is minus RT ln K. I'm not really sure. I took this from a textbook at what temperature this was being done. But you can also get it like an estimate if you say the delta G is basically like the delta H here. We are neglecting the entropy. You could calculate by this equation in equilibrium. And you could see how close this actually is to what you see here experimentally. And you could see how good or how rough our analysis is. So just do this here on your own. So this is the chlorination. And as I say, we could understand this bond is easier to break than this one. So indeed, this should be forming more than the other one. And we have some rough numbers here. So now we do the next experiment. And we do the bromination. And now suddenly we find, wow, it's 2 to 98. What's going on here? If you do again, and let me point out this again, what we are doing here is thermodynamic analysis, and you can probably see where this will go in a second, that we actually need also to learn something about the energy barrier which has to overcome and how this looks like. In the moment we are still doing just thermodynamic analysis, and now we suddenly find that the bromination is much more selective. Well, maybe this is reflected in the thermodynamic analysis. Let's see. The point is, if you do this, so this is for the delta H for the chlorination. If I put the delta H here for the bromination, you will find that this is endothermic. By 14 kcal per mole. So here what we are doing is bromination. And this is 16 kcal per mole. So yes, the one is exothermic, the other one is endothermic. But the thermodynamic analysis shows you that your products, like the bond breaking, bond forming, if you form the secondary radical, it has the same distance, the same difference here to the primary one. And the only reason that we see different overall numbers is that once we are forming HBr, the other time we are forming HCl, and HBr simply has the weaker bond. But the differences are really only reflected here in the radical stabilities. And this is, so no matter where we put the absolute numbers, but the difference here between these two pathways is 2 kcal per mole. So any thermodynamic analysis we should do should more or less predict that the selectivity is equal here. And really it is not. So something else must be going on here. And so what we need to know, what we need to look is really a little bit, have a closer look on the transition states which are leading actually to our radical intermediates. So my first question is, if we do an analysis of here intermediates, we can measure energy and so on. What do we know about transition states? Can we measure energies here or anything? Can we, like the experimental curious? What do we know about transition states? Answer is nothing. At least experimentally, nothing. Our friends in theoretical chemistry can do fancy calculations, but the transition state is not really available for experimental investigation. It's an energy maximum. Let's look again here at our reaction pathway. So if we are interested in the energy barrier, we have to go over the maximum, which is here the transition state. And this is experimentally not accessible. Everything we have here, starting materials, products, also reaction intermediates, they might be very short-lived. So it might be very difficult to do an observation, to do a measurement on them or so. But at least it's in principle possible. The transition state, the energy maximum, we have no possibilities to really get any type of data on that, because it's as the name says, it's a transition, and it's too short-lived that we can experimentally observe it. Physical chemistry is getting better and better, more and more short-lived analysis methods. There have been Nobel Prizes for femtosecond type analysis. So yes, there are some. This statement I made here, the physical chemists start to challenge that type of statement. But again, for the simple organic mind, this is how it is. So we need to do something here. We don't know something about the transition state, but if we look at this selectivity issue, that's really something we would like to know. Because the analysis we made for, let me put again here the chlorination, is that we are running into a reaction where we have our alkane here, and here we have our C-based radical. Now, the one thing we got out of this analysis we did here earlier, wherever it has vanished to, here is that this should be an exothermic process. So the one thing which should be clear to us is if it's exothermic, then the starting point should be higher in energy than the resulting product, or in this case, our intermediate. But we are now in the situation that we need to have to compare two different types of radicals. We're starting from the same alkane. And so we are probably in the situation where we have our primary radical and where we have our secondary radical. So yes, there is an energy difference here. But what we really would like to know is there also an energy difference in the reaction pathway when these are forming? And let me put up the bromination as comparison. So for the bromination, we knew it's endothermic. So we're having something like this. Again, here's our alkane. In this case, plus bromine radical. Here it was alkane plus chlorine radical. And here it's C radical plus HCl. Here it is C radical plus HBr. And here again, we're having a situation that we're going to the same secondary and primary radical intermediate. And so the question is there now any difference here? And now a very important principle comes into play, and it's a postulate. Again, it's a model, it's a theory. And this is the so-called Hammond Postulate. And what does the Hammond Postulate tell us? It tells us we do not know anything about the transition state. But the transition state should resemble the intermediate or the starting material or the product which is closest in energy to it. So in an exothermic case, the Hammond postulate would tell us that this transition state should resemble the starting material more than the products here. So transition state resembles starting materials. By the way, where is our English friend? If I make any spelling mistakes in English, I would like to know. You are in charge of this, more than anyone else. Anyone else can also contribute, but you are in charge. Okay, so the transition state resembles the starting materials. In this case, here we have an endothermic reaction. So this way we will argue that the transition state resembles the products. So why does this help us? Well, here the transition state resembles more the product, so the transition state is more similar to the product, and therefore it really knows about the energy differences, the stability difference of the C radicals we are forming here. This transition state is much more similar to the alkane, which is and our starting radical, which is the same in both instances. So here in this transition state does not really know, in quotes, so much what kind of hydrogen is abstracted. It does not really resemble already the product stabilities here. And so therefore, as a consequence out of this, although the energy difference here between the primary and secondary radical is about 2 kcal per mole in both cases, the transition state differences in the chlorination is smaller than 1 kcal. Calculation. You don't want to go yet. Hey, it's not over yet. And the energy difference here is much higher. It's about 1.5 kcal per mole. So here, the stability of the intermediates is already also reflected in the activation energy of the forming transition states. If you want to have a picture, because organic chemists like a picture, you could just let me bring this to an end, just a second. You could maybe visualize this by having something like in both cases in the chlorination, in the transition state, the bond forming, bond breaking process is not really far advanced. And then the energy maximum is already reached here. So it's not very advanced in both cases in the chlorination. And so therefore the difference of breaking the primary and the secondary bond, simply because the transition state is reached at a very early point when the CH bonds are still pretty much intact. And so therefore the stability difference between a primary C radical and a secondary radical are not really felt. While in the bromination, we have the situation that, let's say, let me also dot this here, that the transition state is only reached when the CH bonds are broken to a significant extent, and in both cases. And so therefore, in the transition state, already the product stability, by the extent how much the bonds are broken, the difference in radical stability is already felt. If you choose theoretical chemistry as your elective, you can very easily do such calculations, because you can, on the reaction pathway, you can calculate such transition states. But simply what you do is, on the computer, you take a chlorine radical and bring it like closer to the hydrogen you want to abstract, and the computer will give you a geometry, and you will see that with the chlorine, the transition state geometry, that the chlorine is still far away and that these still have pretty much normal bond lengths. If you do the same analysis for the bromination, the distance between hydrogen and bromine will much shorter, much more already like the bond, and the carbon-hydrogen bond will be significantly extended, reflecting that it is in the transition state already broken to a good extent. Okay, question?
I would like to know how do you know these differences at the beginning, because you said it was difficult to measure it.
Which differences?
The 1 kcal and the 1.5.
Ah, calculation. Okay. Calculation. Our friends in theoretical chemistry calculate these things. Right? So there are models. Nobel Prizes have been awarded for methods to do calculations of this kind. And nowadays, every PC with free software, you will be able to do this as well. So there are simply computer programs exactly as I said. You put in the two starting materials, you bring them close, and you make an energy profile, and your computer will be able, by looking at all the distances. So basically, the chlorine is taken by the computer around this hydrogen. At some point, it will reach the energy maximum, and this is then a transition state.
So it is just calculus and not
Yeah.
proof?
No. Yeah. But it fits, again, we are talking about models, and an organic chemist is happy as long and everyone is happy as long as the models are explaining the experimental evidence. If then we start getting examples where my models do not fit the experimental evidence again, we need to do something else, right? And again, the computer methods started from started from very different, or started from assumption like bond strengths, where they modeled bonds, like either in the early ways just as like basically feathers or strings, which can be broken, elongated, and basically giving them an energy profile. And now more modern goes into all the electronic, everything one knows on bonds goes into these models. But yes, it's computer calculations. Okay, so what is the consequence of this? The consequence is that in general, the less reactive species, in this case, bromine against chlorine, is the more selective one. Simply because always the Hammond Postulate gives us the model or the answer here that the less selective species goes through the later, the more product-like transition state, and so therefore product stabilities are reflected in the transition state. Okay, let's look at some more reactions. Maybe some reactions you don't know yet, or maybe which you have encountered in the basic organic lecture. So one important radical reaction is dehalogenations of alkyl bromides. The question is, how do I transform a alkyl bromide into the corresponding alkane? And there is a reaction, or there is a reagent which is very useful for these type and many other type of such reactions, and this is tributyl tin hydride. And tributyl tin hydride has the property that upon a radical starter with AIBN, tributyl tin radicals as the start reactions are being formed. And now, very importantly, the tin halide bond, tin bromine in particular, is an extremely stable bond. And so therefore, tin radicals have a very high likelihood to attack halogen atoms rather than anything else which you might find in the molecule. So a typical reaction then therefore is being can be set up that you use a bromoalkane, use a radical starter. I also should point out that typically such reactions have to be run at 60 to 80 degrees, because this is the temperature you need to decompose your radical starter, the AIBN. And then as an outcome, you get the reduction product and tributyl tin bromide. You can again formulate a chain reaction. I would again like to try to do this in this kind of cycle I've shown you earlier. So we have tributyl tin radicals, and the other type of radical is that we have in this case, the hydrocarbon radicals. This is the cycle we have to set up. And as I told you, the starting reaction to form this tributyl tin radical is tributyl tin hydride with AIBN. This is the starting point. And then again, what do we have? The tributyl tin hydride is reacting with our bromoalkane. It will form the radical and tributyl tin bromide. And then this radical will now react with tributyl tin hydride. To form our hydrocarbon and again the tributyl tin radical. Yeah?
Could you please draw the formula of this of this new molecule?
Of tributyl tin hydride? So butyl groups. So we have tin, and then we have 3 butyl groups. And hydride. Right, so Bu is butyl. Three of those and a hydride source. So this works very well. Some other reagents do also this type of chemistry, but this is particularly good. And an especially important application is not so much the reduction to the hydrocarbons, because just keep in mind, do you think that this is in general very useful to reduce a bromoalkane back to the hydrocarbon? Probably not, because you make the bromoalkane usually from the alkane, right? So why should you reduce it back unless you have a very special situation? But this reaction is especially valuable to introduce deuterium into molecules because instead of the tributyl tin hydride, there's the corresponding deuterated compound. And so this way, this gives you a possibility, if you have been able to place at a specific position of your molecule a bromine atom, works also with the chlorine atoms, but bromine is better, you are able to exchange that bromine for a deuterium, and so therefore you are able to label compounds, and that is, for this, it is especially advantageous. So this is a big advantage in this reaction. What is the big disadvantage of these reactions? Does anyone know? Sorry? Does anyone know what is the big disadvantage what people don't like about using these type of reagents, tin reagents, organotin reagents.
Because you have the problem of the halogens and expensive to.
Yeah, the expense is not even so much the problem. The big problem is the toxicity. Organotin compounds are very, very toxic. If you should ever work with organotin compounds, you have to be careful. You have to be extremely careful because they can penetrate, because they are very unpolar, and they can penetrate easily skin. If they are in your body, they can penetrate the blood-brain barrier, and that is not good news. And so it's a big difference. So the tributyl tin hydride and also like the bromides you're forming or the chlorides, they are more ionic. They are not so toxic. In fact, compounds like tributyl tin oxides we have on our money. That is what that's anti-fouling compounds. Actually, on every euro note, you can detect tributyl tin oxide compounds as anti-fouling, antibacterial compounds. It's also used on ships. When you paint a ship with an anti-fouling paint, it's tin compounds, tin oxides. Sorry. So this is okay. So like dibutyl tin oxide, this is more okay because these compounds are more ionic. And so therefore they can, for example, not penetrate blood-brain barriers. And because they are ionics, if you get them in the body, they are water soluble, they are washed out easier. Organotin compounds, which only have like organoresidues and tin residues, are very unpolar. So they are not getting out of your body very easily, and they go into everything. And so that is the big disadvantage of tin compounds. And we like still to use these in the lab because there's very little alternative, and tributyl tin hydride has many other applications rather than just these simple reductions I've just shown you. But they have the big disadvantage of toxicity. And therefore, if you work in industry, if you make a synthesis of a pharmaceutical drug, at no point in the synthesis you are allowed to have a tin reagent in there, because you have to get tin out in such small amounts in the ppm and ppb range, and usually if you have at any point of your synthesis tin compound in there, in the parts per million, parts per billion range, you carry it through the synthesis, and that is not acceptable in a pharmaceutical drug. So very stringent things, and there's a big need to help in organic chemistry to develop alternatives here. And we are doing that not very well. Let me show you another reaction. And this is the second reaction here. Is the desoxygenation of alcohols. So if you are interested in having an alcohol and making a hydrocarbon out of this, do you think this is an important reaction? Why is this important?
Maybe because you can produce alcohols with computers, and then you can reduce the alcohols to normal hydrocarbon.
Yeah. So he says maybe producing some more alcohols and reducing them to the hydrocarbon. And this is going in the exact right direction. Everyone hears about the post-oil area, which we have to enter, right? And everyone, in the moment, our politicians pretend that chemistry can do this. We can use renewable resources and to basically use them in chemistry. But indeed, if you think about compounds like glucose, we have lots of alcohols in there. And what you would ideally like to do is a typical chemical which comes from oil, where we know how to process it, where we know how to use it as fuel, where we know how to make many variable intermediates, is, for example, cyclohexane. So in principle, this is not so bad, right? We're having 6 carbons here. So let's find a way to make from glucose cyclohexane. Very difficult. And very difficult on large scale. You would like to do this on millions of tons. Let me show you in the moment what is the most common way to convert an alcohol to a hydrocarbon. And I think you will agree in a moment that this is this is maybe okay on a small scale, but this is not very practical on a large scale. So the most robust process which we have in the moment to do this type of transformation, there's a lot of development going on for alternatives, but the most robust reaction we know here is the so-called Barton-McCombie deoxygenation. And so what you have to do in order to do this, you take your alcohol and you have to convert it into a derivative, into a so-called xanthogenate. So you have to use sodium hydride. What is sodium hydride doing? It's doing what every good base should do. It is deprotonating the alcohol. And then you have to treat this with CS2. So the thioanalog of carbon dioxide, carbon disulfide. And you are forming this anion. And then in the third step, you trap this anion with methyl iodide to bring the sulfur together here with the methyl. And so then this way you are getting a so-called xanthogenate ester. And you form this. So already the synthesis, if you would consider this, doing this on, let's say, ton scale, is spelling bad news here. CS2, industrially quite okay, but still relatively expensive. Methyl iodide, highly toxic, highly expensive. Large scale, it's not feasible. But we are not at the end yet. So what do you do here with this xanthogenate? Why is this good for deoxygenation? And again, tributyl tin hydride comes into play. And you need a radical starter. And the idea here is tin is not only forming very strong bonds to bromine, it is also forming very strong bonds to sulfur. So the tributyl tin radical, which you are forming here, is very readily attacking the sulfur atom, which then will give you this intermediate here. And again, keep in mind, if you do radical reactions, always check if you react a neutral molecule with a radical, you have to get out somehow again a radical. Don't destroy it. Sometimes in exams or so, people are nervous and so on, so radicals get destroyed or charges get destroyed. Not possible. And this intermediate very easily defragments, because again, this is obviously not too happy, and forming a carbon-oxygen double bond is a very stable affair. So we see fragmentation here between these two parts, and we have a carbon-oxygen bond fission. And this is why this reaction in general is so difficult, because the carbon-oxygen bond is a very stable bond. But this way it works. We are creating a radical. Plus this. And now this radical here can react with a molecule of tributyltin hydride to close the cycle, to have the reduced product, and again the tributyltin radical, which goes back into the reaction. So it works great, good yields, but think about the practicality: stoichiometric sodium hydride, stoichiometric carbon disulfide, stoichiometric methyl iodide, stoichiometric tributyltin hydride. It's completely unpractical if you think about using renewable resources like carbohydrates on large scale to convert it into hydrocarbons, compounds we value as fuels or as starting materials in industry. And if you think about this, there might be a way that our industry might change and find synthetic ways, and they are working on this, from carbohydrates, but everything in the moment, all our chemical industry, all the processes, all the ways we convert compounds, everything is based on oil. And so there's a very large technological gap in the moment to close renewable resources to the oil field. And so if you think, and sometimes you hear chemistry already is a mature science and there's nothing to discover, I would propose this is something, if you're interested in organic chemistry or inorganic chemistry, we need catalysts which basically do this and make carbohydrates and water out of this, right? And that is not on the horizon in the moment. Okay, with this, thanks very much. Tutorial 12:15, I will do the tutorial here. And I know that the biochemists cannot attend for course schedule. There is a second tutorial here from 1 to 3. Is that something that the biochemists can do? Or we have to see. So the biochemistry students, check with me. We need to find a different date for the tutorial for you. If you are wanting to, the tutorial is not mandatory, but 12:15 here in this lecture hall, we will have the tutorial. Okay.